All right. Just a brief discussion on gradient bandits today, which is the final part of the chapter 2 of reinforcement learning by Sutton and Barto. So basically, we can establish a different technique using gradient ascent if instead of considering the Q value, which has a defined relationship to the reward function, we consider a set of values that are relative to each other. So this is a set of values that has no meaning and no impact in terms of the actual reward function, but the relative significance of each one determines the proportionality of choosing that action. So if we consider, for example, using the softmax function, which is just the exponent of each element over the sum of exponents, then we can choose from these values probabilistically. And so if we were to consider, so in order to update, so we can pick easily from this distribution, but in order to update it, we can simply do gradient ascent to maximize the expected reward, because this is really what we care about. This is the number one thing, is maximizing this value. That's all we care about in reinforcement learning. And so we want to take a step in the direction that will maximize this with respect to the values, and that's how we update these values. And so we can write this out. There's a full derivation in the book, which I won't go through here. I'll just give some intuition into it. So this expected value is this is actually the optimal Q value, basically the rewards times the action taken. And keep in mind this pi function, the policy, is a function of the h's because it's a softmax of h. So this is you can see how this derivative exists is because this is a function of that. And so we can see that the derivative of h, for q over here, it's just the reward. And we can see that this derivative is just a derivative of softmax. And so if you're familiar with artificial neural networks, you'll know that the derivative of softmax is for each value in the array. I need to turn down xi1 minus xi is basically what it is. But this is only if this value is chosen. And so that's why there's two possible outcomes. If the value is chosen, then it is 1 minus pi. But if value is not chosen, then this is 0. This becomes 0 if it's not chosen. And this gets canceled out. This term in both cases gets canceled out. You can see in the exact derivation how that's done. But it's specifically because there's an extra pi over here, which results in a division over here, which cancels these out. And so basically we have either this 1 minus or we have negative pi if it's not chosen. So now we can go through the code and we can see standard imports. This is the normal softmax. You can see the exponent over the sum of exponents. However, for reasons of numerical stability, we use this. It's the exact same. You can see just minus a constant. But it's important for 0 values and initial values. And so to get the action, we choose with probability according to each value, according to the softmax function. And we set this up. There's no Q and there's no N. And so we have this H here, and we update the action according to that formula, and we update the actions not taken by the same formula. given in the equation, and we can use a baseline, so we can do this reward minus something, and this is any number that's not dependent on the state or the action. So this is just some value. In this case, it's a running average of the rewards. But it's important to note that this is valuable because it can reduce variance. And you'll see baseline techniques sometimes occur in policy gradients. And so we run this code, and you can see that this is also the alpha value is the learning rate. If we remember, you can go back and see that this alpha value is basically how fast it learns, or is like the learning rate in artificial neural networks. And so we can see here that without a baseline, it achieves subpar. You can see that the green and red are pretty close, but for the higher learning rate, the baseline achieves a better policy because it reduces variance. And that's pretty much it. That's the last part of chapter 2, and that is all that we'll be covering today.